Thank you very much for the introduction, and thank you very much also for the organizers to giving me the opportunity to speak here. So I'd like to survey some work with Eleonora Di Nezza and Lu Qin. It will be mostly a survey, as I said. I will also give a couple of short proofs here and there, just to show everyone that there's mathematics involved. But for the most of the arguments, I'll refer to the paper in the archive that we posted recently. Okay, so for the duration of the talk, we nail into the ground a compact Kähler manifold. Okay, so let's start with something really, really classical at this point, which is Yaos Theorem. Okay, so you're given a smooth function that satisfies a normalizing condition. All right, and it's also positive. And then Yaos theorem aims to solve the following equation. Right, with omega u being non-negative, and as we know, there exists a smooth solution that's polarity subharmonic, smooth, and unique constant. Okay, so as we all know, the generalizations of this result have been quite numerous. Many of us have been involved in different generalizations, so I don't even attempt to give a partial list to make sure I'm not unfair to anybody in the audience, of course. So I'd rather go to our specific generalization that we intend to speak about today, which is to solve this equation when I ask the solution to have a specific singularity type. All right, what does that even mean? So let's make sure we're on the same page. So if you're given two polarity subharmonic functions, right, you can define this equivalence relation, meaning that there exists a big constant big enough so that psi minus c less than phi less than pi plus c. In this case, we say that these two polarity subharmonic functions have the same singularity type. And then the singularity type will be denoted by sort of bracket notation. Okay, so, and then the problem at hand is as follows. So now I'm taking a function f that's non-negative, and ft measure, and I aim to solve the following systems. Okay, so I'm just looking for a polarity subharmonic function now. And I want that my solution has a specific singularity type. So I want that equals to the type of u is equal to the singularity type of some phi, where phi is also part of the data. So I should add it here that phi you fix in the beginning. Okay. Now, I should also note here that in this interpretation, omega u to the n, as well as all products involved, should be interpreted in the terminology of Gedgen-Zeriahi. Right. So during the talk, all right, so omega u is the pluripolar complex Monge-Ampère measure. Yes, of course. Thank you. As defined by Gedgen-Zeriahi. And then believe in 2006. And their construction builds on the local construction of Segrel from before. And again, if you're not familiar with this, then think of it as a generalization of Bedford-Taylor theory. Generalization of complex measure of Bedford-Taylor. In particular, if U happens to be bounded, then this is exactly the Bedford-Taylor complex Monge-Ampère operator. Now, truth to be said, that will not apply to our case because we were exactly looking for, most of the time, a non-bounded phi. So that will, sort of push us into the realm of this more general definition. The good thing with this definition is that it applies to every plurisubharmonic function. Okay, good. So this is the problem. So this is system star. I refer to it throughout the talk. Okay, so to learn how to break the blackboard. So can I push the lower one? No. Okay. And I guess I don't need this. All right. So how do I pick it up again? Is this one? Okay. And I'd rather erase the blackboard now. Okay, so the first remark I want to make that for general phi, unfortunately, this is not a well-posed problem. So for general phi, star is not well posed. And we will see in a minute what's the correct condition. And then to that condition, I need to recall an operator that was defined by Ross and Wittnistrom. So it turns out that if you start with a plurisubharmonic function psi, you can associate a so-called envelope with respect to the singularity of psi. So this is how it's denoted. And this definition is, as many are familiar, is as follows. So you want to take the supremum of plurisubharmonic functions, so phi in, such that phi is non-negative, and also the singularity of phi is exactly equal to that of psi. Okay, so so as we know, supremums of plurisubharmonic functions often are not plurisubharmonic. So you have to take at the very end the upper semi-continuous regularization. So exactly for that reason, I think it's beneficial to take an alternative definition here as the limit of certain increasing plurisubharmonic function. So you take the limit of the following rooftop envelopes. So it's 0. And then C goes to where this is the supremum of all, again, plurisubharmonic functions such that U is less than 0 and U is also less than. Okay. So in the literature, at least in my paper, we often call this a rooftop envelope, right? So this is the greatest plurisubharmonic functions that you can stick under 0 and psi plus C. So obviously the minimum is not plurisubharmonic, but you can still think of this as a minimum of plurisubharmonic functions. So if this is a U, this is a V, then PUV is sort of the greatest omega plurisubharmonic function that you can stick under U and V. Okay, so with this operator in mind, we can formulate the main theorem, I believe. I want to keep the system around for a short while. So we need two conditions on the phi so that we can solve the system star. So main theorem. So if you have phi Fleury subharmonic function, and phi has small unbounded locus. This means that this set, this is completely pluripolar, so complete so you can think of this condition as outside a closed set with no interior. Phi has to be locally bounded, right? So if phi has algebraic singularities or almost algebraic singularities, this is always satisfied. And the second more important condition, phi has to be from the image of this operator. So then star has a solution that's unique up to a constant. Unique up to a constant. So we recover an analog of Yaos theorem. Now a couple comments about, so we have two conditions. For phi, I ask it to have small unbounded locus. So this may be a technical condition. We're not 100% sure about it yet. It is kept around for the reason that without this condition, it's not clear if you can integrate by parts, even in the sense of this more generalized Bedford-Taylor theory of Kedgen-Zeriahi. On the other hand, it gives so this condition, whether technical or not, it gives a sort of a more concrete interpretation of the first equation, right? So what it really means is that outside this bad locus, this equation can be interpreted in the sense of Bedford-Taylor, right? So maybe that should be my first remark. There will be plenty of remarks. So number one, so let this condition, I don't know, maybe A, should be condition B. So condition A allows to interpret star in sense of Bedford-Taylor. It's hard to believe that if, in terms of applications of this theorem, if we will ever need singularity types phi that should be more general than having unbounded locus. Truth to be said, we're looking into it as we speak if this condition can be generalized or not. Okay, so more remarks. So now all the results that I'll be talking about today apply in this context of big cohomology classes as well. All right, so all our results apply for big cohomology classes. If one is dealing with a big cohomology class instead of a Kähler class, in my eye, the main difficulty is that you don't really have a bounded potential to begin with. Now, in this work, that's not a problem. The main aim of this project was to sort of eliminate the need of bounded potentials to begin with. So perhaps it's natural to expect that all our techniques work in the big case, and they actually do. So if you look at the paper that's on the archive, it's all our arguments are given in the context of big cohomology classes. All right. another remark. So when you consider this type of equation, it almost has a sister equation, right? So this one. So historically, right? So when lambda is non-negative here, right? So the treatment of this equation went almost parallel with that one. So there's an analogous result. Exactly the same statement. You replace this equation with this equation. So maybe I want to call this double star. So theorem also holds for this equation. With lambda positive, of course. So it's the exact same theorem, the exact same conditional. Okay. So at this point, you're asking, of course, it's a very natural question to ask. So you probably have a good feeling on the first condition on phi, but you're still wondering a little bit about for what singularity types governed by phi do you have this condition? This operator seems quite abstract. So let me reassure you. So this is my fourth remark, is that if phi has algebraic singularity, right? So it means that locally, phi looks like C log right, where these are holomorphic, then the singularity type of phi is the same as the singularity type of its envelope with respect to phi singularity. So this means what? That pretty much every algebraic singularity type you start with, right? This operator does not give you a lesser singularity. So in that theorem, you can take arbitrary algebraic singularity type, and you will get a unique solution up to a constant, right? So this implies that phi, so if phi has algebraic singularity, then phi, so there, this is probably imprecise. Oh, so I'm going to write it in. So what I mean here is that if phi has algebraic singularity, then you can find a potential in the same singularity class that lies in the image of this P with respect to singularity type. In particular, you can solve this. Maybe this is what I should have written. You can solve this equation with arbitrary algebraic singularity type. Okay, and then maybe a historical remark. So this particular equation. So we were able to find one paper by Fong and Sturm that treated this specific equation. The specific case when singularity type phi is very specific algebraic singularity of green type and slightly general than that. So results by Fong Sturm when phi is of green type. So meaning locally, right? Phi is of right, and you assigned some of these local singularities at a finite number of points, and what they show, if the C constant is small enough, then this equation you can always solve. Now in their case, they're also able to show that their solution is C11, meaning they can bound the Laplacian, right? So solutions. So solution U the Laplace is in L infinity x. So more regular. So it could be that the regularity we obtain, which is basically saying that u is as singular as phi, you can think of that as a C0 estimate. It could be that in this general context, our regularity is optimal. We also believe that if you can, it may be that if there is, I don't know, a C3 representative of this singularity type, it could be that u could be C11 in that case. So what I mean to say is that regularity is inherited from the regularity of phi up to order 2. That is probably the optimal regularity.
Is that regular everywhere?
Yes, C11 everywhere, I believe. So on X. Yeah, of course, away from, right, so away from the singular points, right? So inside the, away from the singular points of phi, it's C11, right? So right here, probably log x minus, right. Okay, so it's, thank you very much. Hopefully it's precise now.
Do you get actual C11 after you use the log resolution and you move the divisor?
I think that's their argument. And then they also state that apparently the argument also works for more general singularities than this, but not quite for every algebraic singularity. But it feels like that kind of argument, maybe after some optimization, could work for general algebraic singularity as well. I'm not sure. So I think it's quite plausible that if your algebraic, if your singularity type is algebraic, then your solution is C11, again, away from the singularity locus. Okay, all right. So maybe one or two more comments. Okay, so a small remark here. So you can consider here, consider more general right-hand side. So, and what I mean by that, so you can put instead of f times, so instead of f times omega to the n, so you can put mu non-pluripolar measure. Right, so I will not go into the details, but in that case, you get a coherent theory, not inside the space of Plur subharmonic functions that have the same singularity type of phi, but rather its relative finite, so its relative full mass class. So in that case, solutions exist and are unique inside this class E x omega phi, which is a generalization of the full mass class of Gedge-Zariahi. So it contains all PSH functions psi that are more singular than phi, but maybe just as singular. So the singularity type can be the same, and their full mass is the same. So it's easy to see that the relative full mass class of the zero potential is the same as the original class of Gedge and Zariahi. So this, maybe many people in the audience are familiar with. Okay, so especially the uniqueness here is sort of playing an important role. I just wanted to mention this. Right, right. So maybe I didn't specify. This is an important condition, and also in Yaos condition. So star has this condition that has, so this is a necessary condition in our equation. So in case of Yaos equation, you need to remove the phi. So in this case, you just get the full mass of d nu on x is, right? So if you have a non-pluripolar measure with the following restriction on its full mass, then star has inside this space that is unique up to a constant. Okay, right. So I've given some examples of how this condition can appear naturally. For example, in the case of algebraic singularities that many people like ourselves are interested in. But you may wonder if this condition is sort of somewhat frivolous and it's just a result of our analysis. Well, I hope to sort of address those concerns in the next result. So it turns out that if you can solve our system star for any f in LP, so better said the following way. So if you take a phi and you can solve it for any right-hand side f in LP, then phi had to be from the image of this operator. So I'll point that out in the next. Right. So take a phi here and just ask that this has small unbounded locus. It's almost like a reverse theorem of our main theorem from here. So if star can be solved for any f in LP, of course with the right normalization condition. So if star can be solved for any f in LP omega to the n, then the singularity type of phi has to be from the image of the operator p with respect to singularity type. So then phi right, so it's more precise to say this, right? And also in this condition here, phrase the problem. Right. Sorry? Yes. No. It's so. What I mean to here is you take the image of the oldies potential and then you take their singularity types. So then phi has to be one of those singularity types. Okay. So let's argument this theorem because it's quite concise. So by contradiction, assume that you can solve star, but phi is not from this set. So by contradiction, assume that you can solve star for any LP, but this is okay. So this implies the following. So in particular, so from here, get the singularity type of phi has to be strictly less than the singularity type of p of phi. It should be strictly less. Right? Because in case they're equal, right, then obviously the singularity type of phi has to be in the right image. Okay. Okay, so some preliminary wisdom should be before I continue the argument here. So I'm going to prove the following claim, hopefully by the end of the talk. It goes like this. So the full mass of phi is always equal to the full mass of p of phi. Okay. So, to be proved. The second claim is about what this measure looks like. So it turns out that you have the following estimate for this measure. So this measure can be estimated with the following one. So this is just a characteristic set of where this operator coincides with 0 times omega to the n. Okay. Now, this, it takes a bit of time to prove. It's a technical argument. But I want to sort of give sort of a heuristical justification of why this is the case. Right? So going on here. Now, if you remember, so recall that this p phi 0, it can be interpreted as a solution of an obstacle type problem, right? So your obstacle is 0, and you're taking a bunch of candidates, potentials that lie below 0 and have the same singularity type of phi, and then you take the soup. Now, in general, so let me just recall that phi the solution of obstacle type problem. Now, for such problem, and this is going back to work of Cartelli in subharmonic potentials, right? So the set where the solution of the obstacle problem agrees with the obstacle, then you have agreement up to order 2. So meaning that not only they agree, but you can expect that derivatives agree there. Now, accepting that heuristic, obviously in the definition of this operator, the second derivatives show up. So you may expect that actually you have here equality on this set, right? Because the 0 potentials, all those have 0 derivatives, so it's natural for this operator to show up here. Now, on the set, so on the set where the obstacle does not agree with the solution of the obstacle problem, so on, right? Expect the potential to be under tension, right? So the condition of plurisubharmonicity should be under tension, right? Which exactly means that the corresponding complex Monge-Ampère operator vanishes there. So with the sort of the philosophy of obstacle problem, on this set, expect that so it's probably better said that this should not be charged. So this set has no charge by this operator. Okay. So with this said, I mean, it made the case that here this estimate isn't actually optimal. It could be that actually have equality here. Now, by results of Ross and Witt-Nystrom in situations where phi is a specific kind of algebraic singularity here, they actually show that you have equality there. So I think this is believable that this estimate holds. Now, as I said, I will prove this later. So now I'll use claim 1 and 2 to finish the argument here. Okay, so now, by claim 2, I get what? I get that this operator, this one, I can write it as f times omega to the n, where f is simply bounded, right? Right, this condition. So if full conjecture, I guess it's true if you have equality here, you can just take f to be the characteristic set of this potential. Now, the theorem said that I can solve, if I put a u here, I can solve this Monge-Ampère equation, right? So by conditions of theorem, right? So the system, so the following system has a unique solution inside this relative full mass class. All right, then again, what's that? So let's call this double star. This is the, so you take this f, right, and you want to solve this equation. You want u to be from and also, yeah, no, just this one. Now, we know what the solution is, right? So the solution is this one. So all we care is about the uniqueness, right? So solution is actually equals p now. Let's, I mean, the whole object was, right, that I supposed that I can solve the same equation with phi here instead of this p of phi. So let's write this down. See, that's a contradiction. So we suppose that this equation also has a solution. Unique. Now, the solutions have to agree because of one. The full mass class, so the full mass of both phi and p phi 0 have to agree. Right, so by claim 1, we get that this potential, this class of potentials, is inside this class of potentials. But unfortunately, because I suppose at the beginning of the proof that phi is not from in here, I get that this specific element, p phi 0, is not inside here. So but then I reach a contradiction, right? Then I cannot solve this because I know from here that the only solution of this equation is this one in this bigger class, right? And then this class is exactly missing the solution, right? So by uniqueness, let me call this triple star. Uniqueness so by triple star cannot have a solution inside so that means that not only can I not have a solution with the same singularity type as phi, but I can't even have a solution in this bigger class, right? So that we have reached a contradiction. So hopefully that sort of addresses the question whether this condition is natural enough. We believe very much so that by this theorem. So this says again, if you can solve the equation for any LP right-hand side, then the singularity type of phi had to be from the image of p phi. Now, so hopefully this justifies the definition. So we call singularity types coming from this set model type, right? So if and only solve the complex Monge-Ampère equation with prescribed singularity type for model type singularity types. Okay. So next, I would like to speak a little bit in the remaining time about actually what goes into proving our main theorem. So it's quite an process, and I want to just touch on sort of the main plan of the proof. So plan of proof for main theorem. So again, main theorem was that from singularities you can solve a complex Monge-Ampère equation. So first by generalizing the variation theory of Berman, Buxom, Gedgen, Zeriyahi, you find a solution in E1. So in the relative E1 class of phi. I'll tell you what that is. So first, generalizing B, B, G, Z, we find a solution for star. Star was the first system. Inside this set E1 x omega phi. So you can call these the class of potential with finite energy relative to phi. So this is all PSH omega PSH functions satisfy this condition. So psi minus, so I just want them from E so trivially, this is inside the relative full mass class. Okay, so to get a solution is not quite the same singularity type as phi, but it's almost that singularity, right? So it's a slightly bigger class. Okay, so next, what you do, you use specifically the fact that your right-hand side, f, is an LP of omega, right? So by generalizing Covert's work, right, via BEGZ, right, you get that phi is even better than this class. It has, your solution U. So let me call this, so solution U for star inside this class. So next, by generalizing colloid J's, C0 estimate via the work of Berman, Esidou, Gedgen, Zeriahi, Buxom, Esidou, Gedgen, Zeriahi. Okay. I want to make sure I get that out right. Okay, so you get that this solution from E1 right. So if you look at this closely, the requirement that phi and u have the same singularity type, that's really a C0 estimate, right, in this context. Okay. 3, for uniqueness, as I said, star you can really generalize to right-hand sides with having a non-pluripolar measures. So uniqueness you show in that context by generalizing Dinev's work. Right? So by generalizing so Dinev's work applies to this class, Gedgen Zeriahi's class. We just have to jump to the relative, right? So the relative version of this family, this one. Okay, so it's quite a tedious process, but it turns out that you can really closely follow each of the steps as in their original work, because what you can do is develop adequate potential theory in these more general classes that sort of mimic the potential theory in this class and also in the E1 version. Let me just remark. So 1, 2, 3 is carried out by developing potential theory for Ex omega phi and also E1 x omega phi. Okay, what I mean is that you find analogs of the comparison principle, dominations principle, etc., and etc. Now, it turns out that to achieve this, you actually have to go a little bit deeper than that. So to successfully develop the potential theory, you actually have to go back to Bedford-Taylor theory. Bedford-Taylor theory applies to bounded potentials. So you have to extend some of the main convergence results of Bedford-Taylor theory to apply for general PSH functions, and instead of the Bedford-Taylor complex Monge-Ampère measure, to apply for Gedgen-Zeriahi's non-pluripolar measure. So I'd rather talk about that for a minute. So what you have to generalize and then develop the potential theory. So this is achieved generalizing limit theorems of Bedford-Taylor theory. And I want to specifically focus on one limit theorem that sort of collects everything. Okay, so suppose you have m sequences of harmonic functions. So J runs between 1 and n. And we ask that each of these has a limit where this convergence is either decreasing or increasing almost everywhere. So it's either or increasing okay, so in that case, the classical, oh, sorry, what I meant is a k here, and convergence is as j goes to infinity. Okay, now classical Bedford-Taylor theory would tell you, right, in case everything is bounded, that these mixed masses, so sorry, phi 1, converge weakly to these right? So this is what Bedford-Taylor theory would tell you in case everything is uniformly bounded. Now, we know that in general this cannot hold, so obviously there should be something that I add into this missing space, and that's exactly the case. The question is what to add. Now, the good thing here is that we're on a compact manifold. So it turns out that if you have a semi-continuity assumption on the full mass of the space with respect to all these non-pluripolar products, then this is true. So what's the condition? This is, I'll call it condition plus. So if condition plus holds, which you take the full mass of the limit, is greater or equal than the lim sup on J then this holds. Now, notice that in case of Bedford-Taylor theory, when everything is bounded, right, we know by a generalization of Stokes that actually all of these just simply equal integral of omega to the n, right? Now, in case of general plurisubharmonic functions, this is not true, so that you need to impose this. Okay, so this is one of the sort of the basic elements of Bedford-Taylor theory that so you need to rehole and use it in the development of potential theory. Something else. So let me call this theorem 1. Now, it was conjectured by Buxom, Esidug, Zeriahi, hopefully I got that right now, so that you have monotonicity of full masses of non-pluripolar products in terms of singularity types. And then we're also able to establish this, building on a recent result of Witt-Nystrom that establishes a particular case. So what do I mean? So if you have harmonic functions, uj and vj, and the singularity types of the uj's are less than the singularity types of the vj's, then the full masses of the non-pluripolar products okay. So in case of big cohomology classes, this was conjectured by BEGZ. And then, as I told you, everything I say actually is written in the context of big cohomology classes in the paper. So this verifies a conjecture of BEGZ. Now, I can't emphasize enough that our proof builds on this recent progress done by David Witt-Nystrom. So what did he exactly prove? So he proved this same result when all the u's agree and all the v's agree. No, in this context we don't. So you really need the small unbounded locus condition in our theorem. in one specific point, when you generalize the variational theory of BBGZ, right? As it often necessary in variational proofs, you need integration by parts. And at this point, we can't live without integration by parts. So if that somehow would be generalized, the integration parts of, I think it's in BEGZ, right? Then it's possible that we can remove the small unboundedness condition. It's used also in other parts, but I think in that case, it's sort of mostly convenience. The main burden is the fact that we need to integrate by parts. It's just, fact of life at this point. So, theorem 2 generalizes theorem of Witt-Nystrom, right? So again, in his result, U1 is equal to U2, so equal to UN, and V1 is equal to V2. Okay, now a corollary of theorem 2, so corollary actually two corollaries. So because of this monotonicity condition, if in theorem 1 you have an increasing sequence of potentials, okay, sorry, so let me just, so in this case, you have condition plus is automatically satisfied. Okay, so yes, so if you condition plus is automatically satisfied, if phi j k increase to phi k for all k. So I wanted to prove corollary 2, but I will just state it and then finish it up. So there's also corollary 2. So I promised to prove a claim at the beginning of the talk. So that was omega phi to the n is always equal to omega p phi to the n. Now, yes, of course, sorry. Hurry. So how do you show this using theorem 1? So by theorem 1, this is simply equal to limit j, maybe a c. So limit as c goes to infinity of the right? Because in the beginning, I told you that you can interpret this as the increasing limit of these potentials. Now, it's easy to see that the singularity type of these potentials is the same as the singularity type of phi, right? So you just get that this is limit as c goes to, right? The limit doesn't depend on phi anymore. Okay, so since I'm out of time, sorry for extending all your patience. Thank you very much.